Alright, in this video, we will do some derivative applications. And, I don't know, should make sense. So here's what we have. So before I even start with derivatives, let's just go right into what is a zero. If you already know this stuff, you could skip ahead, but I think it will be useful regardless. So we have x-axis and our y-axis. And we want to talk about zeros. There's two ways to talk about functions, I would say. So let's say there's a function. So it's just, I don't know, some random function. I don't really know. Let's talk about f of x. All right. So there's two things you can generally do with f of x. You could have an x value and plug it in to get a point. Nice. Now, what about this though? What if you had a y value? Could you plug that in to get a point? You certainly could. The only thing to watch out for is when these overlap and such, because at this point it has multiple values. In fact, it has 3 values, how I drew this graph. So that's the only hard feature about doing this kind of stuff. So that's the idea. All right, you can either have a y value, so a value for f of x, or you could have a value for x, the value plug into f of x. If you have a value for x, it's more versatile because that's how the function is set up. But if you have a value for f of x, you can still solve these things. Sometimes they're harder, but still more than possible. So one thing that we study a lot in algebra is parabolas. That is some kind of ax squared plus bx plus c. Anything where you square a number, then you add it to something multiplied times that number, and add it to some c value. Now this is a random curve. I'm not going to say this is 0 because I don't want to define a, b, and c as anything. I want to just let it be arbitrary for you. So let's go into this. So how would you solve this thing for 0? Well, guess what? We'd say that f of x, we're going to say that's the function, not the same function as this, we're going to call this f of x, is equal to ax squared plus bx plus c. All right? That is the first thing. And now here's that crazy step I'm going to do. So we can have x values and plug them in and get results. But what if we had a y value? Well, one very important y value that shows up all over mathematics, is 0. 0 and 1 are like the best numbers to look for in many functions. But 0 particularly, because multiplying by 0 is the same result as dividing by it. Well, no, my bad. Don't say that. Don't. Multiplying by 0 warrants the same 0 value. And so there's all sorts of value in being able to find when something equals 0. So how do you find these points? Well, this is whenever the y value on this line is 0. This point is a 0, and this point is 0, because that's when the curve equals 0. So here's what we do. We set this equal to 0. And we're like, okay, so now we have only x's of b and c. A, b, and c are just numbers. So this could be an arbitrary scenario. And if you remember algebra pretty well, sorry, you'll know that there are 2 answers for this, as there should be. There's 2 answers on most parabolas. And it's found by this formula. Negative b plus or minus b squared. Is it plus? No, it's minus 4ac. All over 2a. And that solves for the 2 zeros. So we can solve any parabola with it. And that's called the quadratic formula because it's a quadratic equation. That exists just to solve things like this. If you did standard algebraic methods, it would be really hard to solve. In fact, I would call it advanced algebraic methods in order to solve for x. Because they're just, how do you get x's by themselves? It's a matter of factoring all sorts of things. It's a quadratic equation or formula, whatever. And this was discovered quite a while ago. Man, I should put years on these things, but I'm pretty sure it was before 1500. that we knew how to solve these things. But then that brought out the cubic, which had like all sorts of challenges in order to solve these. And by the way, let's say you're solving for a different value. We know how to solve for zeros, but how do we solve for different values? Guess what? It's not actually much more complicated. Let's say we want to solve for when this curve equals 1. So this whole line right here. We're just going to say that's 1 for now. How do you solve for these 2 points? Guess what? Set this equal to 1. And if you set equal to 1, there's no equation for this. Right? No equation. Except, let's see. Wait. What if I subtract 1? Alright, so 1 minus 1 is 0. And then subtract 1 on this side, you just subtract 1. And I'm going to do a quick little thing. I'm going to put this in parentheses, c minus 1. Because these are just both numbers that are added onto here. Guess what? This is just the c term, and we just have to replace the c term with c minus 1. And we can solve any equation using our equation that solves zeros. So this equation is insanely versatile. I like that word. So this is how you solve a lot of actually minimum and maximum problems, which is actually what we're covering in this video. Yay. All right, so that's the idea of zeros and solving for these. It turns out lots of things can be turned into things that are easy to solve when they're equal to 0. So that's the thing to keep in mind. Let's keep going here. And yeah, I said I'd prove quadratic formula in another video. I really want to prove it. So, all right, let's get started. Move this aside a little bit. Sorry, I need to grab my markers so they don't write all over the place. All right, so here we go. We're going to talk about maximums and minimums. And I touched on this a bit in the last video. But this is the idea. So you have a curve. You have these are axes, whatever. X and our y-axis. All right. And you have a curve f of x. I'm going to draw it kind of specifically. All right. That is our curve. I'll put arrows on it, but that doesn't really matter. Now here is our curve. Let's label it f of x. Now what is f of x? We're not going to define it because we're just talking about minimums and maximums. You'll see in a second where that 0 thing will come in handy. So when are there minimums and maximums? You can look at a curve and be like, oh, here's one and here's one. Done. And then put your marker down and just leave, and you're happy. You're on your way. But graphs are nice tools, but they're not always handy with you. And it's not like you can just tell like a computer, oh, graph this and then look at it for a second. Do you see? That's a max. Like, that's kind of complicated. You can't just tell it to solve for that, like, somehow. You have to do it using equations and such. Now, there's probably some futuristic computer that can solve this, but let's pretend there isn't for a second. So that's a max, that's a min. And what's special about these points that we identified? Well, both of these points have slopes of 0. Check that out. And we know how to solve for slopes. That is the slope equation for this formula, which is just the derivative. The derivative of our f of x. Let's put an equal sign. F prime of x. So you plug in an x value and you get the slope at that point. Awesome. So, but if that can solve, if you set that equal to 0 and solve for it, there's one other spot where it's a 0 slope. Let's follow it. Oh, second spot. Follow it. Third spot. Wait a minute. What's up with this guy? This is also a 0 on the equation, technically. What's up with that? What is that? Like, it's not max or a min. It's not increasing or decreasing. What is what is that? So let's talk about this. How do you know, first of all, how do you know what is a min and max numerically? And I'm going to actually use a graph to prove this, which is almost ironic because I talked about numerically, but it'll make sense. Well, this is when the equation is 0. But if you look here, what is the slope doing? It's going from positive, 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 positive to negative, 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 negative. All right, so that means our slope equation will look something like, just guessing here, bam, there. And then here it's going from negative to positive. So it's going to flip right here, go from negative to positive. Yep, goes to that point. Now this point, what's going on here? That's a little weird. That's going positive, 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 positive. Still positive, 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 and then positive, positive, positive. It's all positive. So we're gonna, but it's 0 here. So we have to bounce on 0 and go back up. Yay, now we have our equation. So this is what we call f prime of x. Now one more equation to graph, and that is the second derivative, because that is our trick for finding this. So if you graph second derivative, what's happening here? It's a negative number. What's happening here? It's a positive number. It's a positive slope. Let's put it up here. And what's happening here? That's a 0 slope, because that's 0 as well. What's happening here? That's also a 0 slope. And this is a positive slope. And this is a negative slope. So it looks like we have a lot of negative slope over here. So here we go. Here's our equation. Second derivative. It goes through there. Just bear with me here. All right, and then it goes down here, and then it goes up here. Something like that. We don't have to be super precise here, because what we actually care about is just the value. So what did we notice earlier? We noticed that when this second derivative value is negative, below the axis over here, then a max occurs. And that makes sense, because during this whole period of time, the slope, the speed of this curve is decreasing. Then over here, oh, whoa, look at that, look at that. That happens when this curve is, we say it's during this whole period of time, it's increasing, and we call that a min. So minimum is when f prime prime of x, double prime, second derivative, slope of the slope, acceleration, whatever you want to call it. If that is negative, that tells us what about the curve at that point? Let's call it x1. Let's call that x1 so we know we're talking about that specific point. If that's negative value, I don't really care what the value is. If it's negative in general, we know that that's going to be a max. Sorry, I meant to talk about min. This is x1. This is going to be our x2. So, and then f prime prime of x2 is positive at this point. And so that tells us that's a min. Now, what about this weird case? What's happening there? If you look at second derivative, follow it. What happens here? They overlap. The slope here is 0, while the second derivative is also 0. So if f double prime of x, let's call this x3, that's point on the line, of x3 is equal to what? 0. And of course, all these points we're saying that x1, x2, and x3 also make f prime of x equal to 0. That's why we even selected them in the first place. But when this happens, we call it neither. And it should make sense what's going on here, because usually you have a curve going like this. But if the mins and maxes come closer together, what happens? They kind of cancel out. You get something like that. Sorry, I had to skip to that side. See that progression? As the mins and maxes go towards each other. That's almost like a wave. They just cancel out and then become neither, but it's still known as it's actually called an inflection point. When this thing is 0, we reflect, we inflect, whatever you want to call it. Those are also inflection points on this curve. You can see that's kind of when we're switching from speeding up to speeding down. Also here. You can always see that is where this curve is 0. Now there's a bunch of circles, all sorts of fancy little stuff here, but don't worry. Next page. So we're moving on, and now we can actually apply our knowledge to, let's try a real problem. Let's try a parabola. And you know what? I just love arbitrary things, like things that you can make arbitrary. I call it arbitrary all the time, but I more mean like abstract, because you can place any variable into this formula. Ax squared plus bx plus c equals f of x. All right. So that's our curve, and it will look like this. It will look like this. It will look like skinny one. It will look like a very skinny one, or it will be a really wide parabola. All sorts of things. These are all represented by this kind of equation with different a's, b's, and c's. A kind of affects the width, B kind of affects the placement, and C kind of affects how high up and down it is. They all kind of come hand in hand. All right. So but all of these curves have maxes or mins. So first off, when do they occur? Well, they occur when the second derivative is equal to 0. And what is the second derivative of this equation? The second derivative is derivative of x squared. A is just a number, so it's just 2ax. Derivative of that is b times 1, whatever. Derivative of that, 0. All right. This is actually the home stretch. So if 0 equals 2ax plus b, what is the x value that makes the slope 0? Because that's what we're solving for. Just subtract b, so you subtract b, and we get 2ax equals negative b. And now divide by 2a, and you get x all by itself, all lonely on one side. But we actually like when x is lonely. It'd be funny enough, because it has all the support from over here. It's in the spotlight. That's what I like to think, actually. So negative b over 2a is, the word for this is extrema. If we don't know whether it's a max, min, or inflection point, that point when it goes like this, we just call it flat out extrema. Here we go. What's so special about extrema? What's so special about extrema? What so special about extrema? Oh, I already wrote extrema. So what's this? Whatever. What's so special about them? Well, we care a lot about when things hit extremes. So that's just the vague sense. And now, guess what? We can just also take the second derivative, and now we can find what kind of extrema that point is. So if we plug that equation in, negative b over 2a, into this equation, well, negative b, you have to plug it in the place. So by the way, let's actually take the second derivative first, so we can actually plug into it. What's the derivative of this? B is 0. 2ax is just 2a. That's the slope of x. All right. So that is our equation. So 2a. So let's plug in x. Well, this has no x in it, so we don't have to plug in x. It's always going to be 2a. And is 2a positive or negative? Well, here's how to find. Is a negative? If a is negative, let's just say that, then what happens? Well, we know that says that acceleration, or this value, is decreasing this whole time, so you get a maximum because it's at the top of the curve, decreasing the whole time. So that is a max. So if we have negative b over 2a and we get an x value, that tells us x value, how do we check? Well, if the a value of this equation is negative, it's a max. And if it's positive, the exact opposite, min. Now I'll tell you right now, this can... Well, actually, it could be 0. But I'm not gonna get into that so much. If this was 0, though, this whole term would disappear, so it gets a little trivial. But we know that positive, min, negative, max. All right, we good? Yeah. And let's finish up with one where we actually have to use the quadratic formula. Just put some use to it. All right. All right, we're almost done here. All right, so if we know quadratic formula happens when you have kind of an x squared kind of case, something with x squared in it, and we want to take the derivative of something that becomes x squared so we can solve this for 0. So, and by the way, this is my thought process right here, because I'm trying to create a problem that has an x squared going to 0. Guess what? We have one right in our hands. An x to the 3. So we're going to call it ax to the 3 plus bx squared. Now, actually, let's call it a specific function. Let's be specific here. Let's make up some numbers. 2x to the 3 plus 4x squared plus, let's just say x minus 5. We don't care when this guy equals 0. And by the way, if we did care when it equals 0, try that for yourself. It's not very easy to calculate this. In fact, I would say it's very close to impossible, but we have ways to do it. That's something else. Let's just keep going here. What's the derivative? We can just take the derivative of everything one at a time. Derivative 2x to the 3 is 3 times 2, 6. X decrease to the power 2. Bring down 2. 2 times 4 is 8. 8 times x. The derivative, the slope of this equation basically is 1, and that's 0. So now we have that. Let's just get our second derivative right out of the way. So bring down the 2. 2 times 6 is 12. 12x. Derivative of that is 0. Derivative of this is just 8. That's the slope of that. So now we have 3 equations. All right. So now, when does this equation have a max or min? And does it even have either? Let's find out. Does this ever equal 0? Well, let's see. Let's plug in the quadratic formula. And by the way, if something plugs in quadratic formula and you get a negative square root, imaginary numbers, you can work with imaginary numbers, but technically it doesn't really equal 0 at that point, in the sense that we didn't plug in a real number, that is, into here. I'm not going to diss the imaginary numbers. They're awesome, but if you get an imaginary number when you plug in this quadratic formula, you did something wrong. So negative 8, we're just solving this for 0. When the derivative is 0. So negative 8, so that's negative b, plus or minus, because there's 2 results, b squared, that's 8 squared, 64, minus 4ac. 4 times 6 is 48, times 1 is just 48. Yeah, 4 times 6, am I right? No, 24, wow. I need to practice that. 64 minus 24. And I picked this problem out of the blue, so if it works out nicely, wow, I'll be happy. But I doubt it will. Yeah, it equals square root of 40. That won't simplify nicely. And then we divide by 2a. 2 times 6 is 12. All right, let's simplify this. So that's negative 8. Let's keep that there. That's an 8, my bad. Square root of, what's 64 minus 24? That's 40. And let's rewrite 40. Nah, I'll do that in a second. Divide by 12 still. 40 is the same as 4, square root of 4, times square root of 10. And why did I do that? Because we know what the square root of 4 is. Square root of 4 is 2. Oops. All right. So now, and by the way, this equals the x value, that makes it 0. So last step, this becomes 2. And now everything in here is a multiple of 2, so you can divide it. So 2 goes away if we divide by 2. This becomes 4, negative 4 that is. And this becomes 6 if we divide everything here by 2. And we can do that because we have top and bottom to divide. So now we have negative 4 plus or minus, why did I write b? 4 plus or minus square root of 10, that's a number, over 6. It's the value when you make this positive, and also the value when you make this negative. Those are the 2 points. Now, how do we know if plugging those in is a min or a max? Plug it into here. Let's plug these x values in. So, let's call this x1 and 2. Sure, let's call the 2 the negative version of this. 1 and 2. Because it's 2 of them. Positive and negative. We already said that. So let's say x1. If this is positive, then we have negative 4 plus square root of 10. All divided by 6. And then that's in the place of x. And then we multiply that times 12. Actually simplifies 6 times, 12 divided by 6 is 2. So let's just rewrite this as times 2. And then we add 8. Now, let's just think for a second. Will this result be positive? If we multiply this by 2, this is going to be negative 4 times 2, which is 8. Negative 8 is positive 8. That cancels out. And all we're left with is a positive square root of 10 times 2. And by the way, if you notice, that's actually the same thing. as square root of 40. But that's just coincidence or something. I don't know. But this is the key distinction. We got a positive number. What does that tell us? That means it's increasing this whole time. So it's going from here to here. That gives us a minimum. So x1 is our minimum. Now x2 is if we make it negative. And you can already see what's happening. If we make this negative, what happens is you multiply 2 times the negative square root of 10. Guess what you get? You get a negative altogether for the same derivative. So that means that x2 is a max, because during that whole period of a maximum, it's always decreasing. We're done. Thanks for watching.